Oh, sorry. Okay. Is it working now? Great. So we released the initial version of our Stratosphere system this spring under the Apache open source license. And with this demo, we would like to give you an idea of the capabilities of this release of the system. We have implemented multiple data analysis tasks from several different domains. And here we present 2 tasks from 2 specific domains, which are graph algorithms and relational queries. We explain how these tasks can be fit into our data parallel programming model, and we show some code so that you see how PACT jobs can be implemented. And then we run our tasks on a small cloud system which we have installed at TU Berlin. Good. I would like to start with a data analysis task from the domain of graph algorithms, namely the triangle enumeration algorithm. Triangle enumeration identifies triples of nodes which are pairwise connected. So that means that the edges of them form a triangle. And this is mainly a preprocessing step that is used by other methods to identify strongly connected subgraphs known as trusses or cliques in larger graphs. And these methods, in turn, are often used for analytics or analysis of social networks. What the triangle enumeration algorithm is doing, just as a brief introduction, as input, it takes a set of undirected edges from an undirected graph. And for our example, which I will show you later, we took RDF data from the Billion Triple Challenge dataset of this year. So here in the following slides, you will see the steps the algorithm goes through to achieve this goal to find triangles in a graph. And the first thing is that it takes an input, which is a set of undirected edges. It would also be possible to take directed edges, but therefore we would need more preprocessing steps, and we avoid this here just for simplicity. Good. The second step is that all the edges which we've got are projected to the node that is in the lexicographical order, the lower one in the edge. So, for example, if we would have the edge 2, 1 or 1, 2, we would project it to the node 1. The third step would then be to combine all edges that share a common first node that are projected to the same node, so that we can get connected edges that, for example, you might see that we had the edge 1, 2. Let's say 2, which could we take? Let's take 4, 5, and 4, 8. And these could be connected to something called a triad, which is an open triangle. One edge is still missing. This is what we get from this third step. And the last step is then to find all the missing edges for the triads. So that we close the triad and construct a complete triangle. The PACT job that is created in this way looks like this. The input is the edges I've just mentioned. And I think I will show you the code first, and then again the plan, so you know what it is mainly about. Are there questions up to this point? Okay. So this is the source code for our triangle enumeration algorithm, the job. I just go through it quickly. The first things we have here are utility classes that represent our edges and how they can be constructed. we have something like an edge list. And then we have so-called input formats and output formats, which convert the edges, which we get from our RDF input data, convert them to the internal representation of edges. And also, the output format is then used to write our triangles to an output file. This is the output format then. People who have written Hadoop jobs should be very familiar with these kind of things, input formats, output formats, how a job is configured. It works similar. Also, the contracts are written in kind of the same way. We use other input and output formats, and the job is configured in another way because we use this dynamic acyclic graph data flow, and so we are more flexible in putting our contracts together. I'll show you at the bottom of the file how this looks like. Here then we get to our contracts. This is the map contract, which represents the second step of our algorithm that maps the edges or projects the edges to the nodes that are lexicographically the first ones that are incident to the edge. From the, assume the 1, 2 edge, that would be the first, the node 1. Here we get as input an edge and null, which are our input edges, and we create something like that we have the first part of the edge, and the value is the complete edge then. And this, the output of this map contract, is then the input of a match contract. And this match contract takes the output of this map as both of its inputs. I explained it to you later why this is done. And in this match contract, all the edges that have the node that are projected to a certain node are combined with that node of another edge. So the edges are combined with this connecting node that they were projected to. And in this way, we only create triads that are promising candidates for later building triangles. And we don't produce duplicate triangles, triads, for example, with the nodes 4, 8, 4, 5, and 4, 5, 4, 8, something like that. We only have this tried once. And the output is done. What do you see it here? The key is the edge that is still missing for this triad. And the value is are the edges that are already inside the triad. And the way we combine the triad with the missing edges now is that we use a third contract, a second match, which is this, called closed triads, which has as one input the original edges we've got from the input file, and as second input the triads we've just generated with the first match contract. And as in the match contract, always the key value pairs are joined that share the same key. We get all the triads that are missing exactly the edges that we get from the original output file. And this way we can close our triads and create the triangles, which are then output to our data sink. Good. This is mainly represented here. And the reason why we normally the match contract has two inputs. The reason why we put the output key values pairs to the match contract in both of its inputs is that this is mainly something like a self-join, which we can represent as a self-match. Good. Then I would suggest that we can start and see a little demo of this task.
So I believe nobody now camera downloads too much stuff on UMTS, because otherwise we will have to move to a laptop version of the demo, which would show probably 2 nodes running or something like that.
This is the user interface. What you can see on the left side is a set of jobs the user can upload and then select so that they can be run. Here at the bottom side, you can give some parameters to the jobs. What I do here is that I set the number of subtasks for this task to 16, so that the degree of parallelization will be 16. And also what we see here is that we have an input file which consists of the edges we want to combine to triangles, and an output file where we've written the triangles to. These paths are in an HDFS file system, which the Hadoop distributed file system, which you have heard earlier about. Good. You will see this plan more clearly on the next page, so don't say something about it now. Good. So here I would like to mention 4 things. What you see here in the orange circles are our data source and data sink. These are sitting in the HDFS distributed file system, so that where our input data is split into several files, which are read by the map tasks and then later written by the match tasks. Good. The green rectangles represent our contracts, which are the map contract. They're in the first position, which assigns the keys of the edges in a way that, as said, each edge gets as key the node that is in the lexicographical lower position of its incident nodes. Then we have the match contract, which builds the triads, and the second match contract, which closes the triads with the original input data. What we also see here is that we have connections between the contracts, the data sink and data source, so that all of them are connected to form something like a dynamic data flow. And also what is written here is which kind of channel we use to connect these data sink sources and contracts. For example, the first will be a memory channel, and as there's no data transfer needed between nodes, and then we have network channels where a partition is needed to transfer some data between all the subtasks we have. Here we will have 16 subtasks, so maybe some data must be shared or broadcasted, replicated among these. Good, and in the end, the memory channel is again used to write the data to a buffer that is then written to HDFS. So let's run this. Okay, this. Maybe I need a few seconds. This is a job I ran earlier, and it's kind of difficult to make a double click over the internet. Okay, good, great. So what you see here is we have all the different parts of our job, which were the data source, the first map, the first match, the second match, and the data sink. And all the several different small boxes represent the 16 instances we have created. Light blue means, is that right blue? Well, it's light blue. Means that the task is finishing, so that it mainly did its job, but another contract that is subsequent to it still needs other data to start. Dark blue means everything is finished and also the subsequent contracts got its data. Green means there's still work to do. Also what you see here is how these instances are connected by the channels we used. Here we have memory channels, network channels, and again memory channels. Right. What you can also see on a per task level is how long the task waited to receive data from earlier contracts, and how long it's processing, how many resources it's using, and how long it needed to process its workload. What you see at the bottom side is aggregated utilization or monitoring data over the whole cluster. So how much CPU, memory, and network resources were used all over the job. Good. I think that should take another minute or so.
Yeah, it seems slowly completing.
Other questions regarding this? What you can also see here is just below the boxes and above the boxes, we have so-called input gates, where you see how much data got into this subtask and how much data went out of it. Anything else to mention? Yes? Oh, there are questions.
Okay.
Marius?
You mentioned between your data source and the first map step, you have this memory channel.
Right.
Forwarding. But this illustration makes me assume that you distribute data from your data source to different subtabs.
I must say that this representation is a bit misleading, as also, as I mentioned, data from the data source gets also to the second match. And these lines don't make a difference. It's not visible here whether this is connected to this one or if there's a line connecting these two guys.
So the lines for the network channel to the second match or whatever are...
That is correct.
We'll probably see it in a more clean way in the next example.
Right.
These darker bars, are they changing over time? Or which is the semantics of having the darker bar like on top and the bottom and then on both sides and then...
You mean these bars?
Yeah.
So all small boxes that are inside such a bar represent, for example, these are all the map subtasks. And these are all the match subtasks from the first match that creates the triads. And these are all from the second match tasks, which build the triangles from triads and edges. So they are all of the same sort.
And if the bar is on top, then it's like the source, and if it's on the bottom, then it's the sink, or?
Bottom is source, top is sink.
So the dark, I think the question's about the dark blue
Yes.
small part of each of the boxes. So they're small, where the communication
Ah.
comes out.
Yes,
These
indeed.
things.
Yeah.
Right, these represent the communication.
Okay.
Right.
The interface. Like, okay.
Okay, so this task is finished. So I think we can proceed to our second example, which is a TPCH query 3, I guess. And Matthias will show you more detailed information about which kind of parameters you can change during the submission of a job and how these parameters affect things that can be exploited to optimize the execution plan.
Okay, thanks. Do I need the mic?
Yeah.
Yes, you need it.
Okay, thanks, Thomas. So I will now go more into a relational kind of query. So we are using the TPCH query 3. Probably you will know it. It's very commonly used for benchmarking databases, relational databases. And what we actually did is taking the query and translate it to our PACT paradigm. I will just shortly give you the SQL query as this. So we have two tables, orders and line item, and what we actually do is we're having some filtering on the order side, we have a projection on the line item side, and then we're joining those two together. And then in the end we have an aggregation, so we're building a sum over extended price grouped on the order key, which we are also joining, and additionally to the shipping priority. So how do we get from this SQL query to our PACT plan? So actually it looks quite a little bit like the representation you would use when you're expressing this query in relational algebra. So we have two inputs here. On the one hand, the orders, and on the other hand, the line item. And the orders is we can say we have a unique key for this, because we're extracting from our orders the orders key in our file input in our input format, and we are also doing this in our line item. But for line item, this is a foreign key to orders, and so we cannot say it's unique. But on the order side, we know this because this is given by our scheme. So we can additionally mark this is a unique key for our order side, and we can later on use this knowledge for additional optimization. So then we are having those. We are having those two map contracts where we actually say, okay, we filter the map side on the one hand, and we project the line item on the other side. So we have those map phases separated. And in MapReduce, you would probably merge those two maps. But in our system, as we can represent much more complex data flows, we can split those apart and have a much better abstraction of this. So we can see those two separate pipelines also in our plan. And additionally, we say, okay, we have knowledge about our function which is inside our mapping phase. And as we already heard, we can annotate this with some output contracts. For example, this could be, in this case, we annotate it with a same key. So this means within our user-defined function, we do not change our key. So also, this also points to the optimization topic. This is also which we do here by hand, but if you're using any higher level language, you could automatically annotate something like this. And then when we have these two map phases done, we want to do the actual join. So as you heard before, doing your join in MapReduce, you would actually decide for any of those strategies and then implement either a reduced side join where you tag your inputs and then do your join on the reduced side, or otherwise you do your map side join probably where you just take all your data of the one side, store it in distributed cache, and then load it on the other side. So, but when you use this approach, you actually have to hard code your strategy which you want to use when you're doing your join. So what we are actually doing is we're just using our match contract, and our match contract is defined as where we get always pairs of values which have the same key. So this is the actual semantics of a join. And within our join, our match contract, we have as a user-defined function only to concatenate those two tuples which we get. So this is much more less overhead than we had to do for MapReduce or Hadoop. And an additional output contract here is the super key. Super key means that we produce from our input key a key which is, or our input key is a subset of our output key. So we just, in this example, we had for our input in the join, our order key, and we say, okay, when we're now doing our aggregation afterwards, we want to do our aggregation based on the group representing order key and shipping priority together. So we want a new key consisting of order key and shipping priority. And we can say this is a super key of our input, which will be also very important for our optimization afterwards. And then what we actually do is our second reduce. So we have also a combiner where we partially compute our sums, and in the actual reduce step we do the final aggregation. So as I mentioned before, in MapReduce this would be actually two programs. One is just doing your join, may it be map side join, reduce side join, and the other one is then doing the aggregation and calculating the sum. So we all represent this within one plan and can now do some optimizations on this. And I want to show you some of those which we can do in the demo. But before, I also want to show you some code. Sorry.
Isn't the match function here very similar to the shuffle function we have seen in MapReduce? I mean, the shuffle function also, as I remember, does the same thing.
Your shuffle function takes the output of the map contract, sorts it, and then gives it to the reducer. And you also do your partitioning, okay? But the problem is that you have to make sure beforehand what is your key within your shuffle phase, and what data do you send through the shuffle phase. So when you're doing your map side join, you take one relation, store it in distributed cache, and through your shuffle phase there will only be your other relation, and only this one is sorted, and afterwards you take the other one from your distributed cache. And when you do your reduce side join, then you tag both of your components. You need some additional partitioning function, your own comparator, where you can say, okay, I want to have different keys for my order side and my line item side, but so that I can distinguish those two inputs. But what I actually want to have is having all the keys in my same reduce call. So I have to hardwire this some kind. And of course, we are also doing our shuffling phase here in our match. So for regarding on which strategy we use, for example, if we decide to repartition both inputs, then we partition both, send it over network, sort it. We also do this, yeah, of course, you need this. But it's just a way of having more flexibility. Okay, thanks. So coming to TPCH query, yeah, I guess you have already seen most of it. So what we're doing, for example, in our match is just we concatenate our two tuples. We do not have to care about all this other stuff with tagging and so on. And I told you about output contract. So how do we annotate this within our source code? We have just those Java annotation where we can write to our Java classes at superkey, and then the compiler knows, okay, I will have a superkey for this class, and I can use this knowledge further on. Yeah, I guess the rest of the code is very straightforward.
How do you compute the superkey? How do you guarantee that the superkey is unique?
Not at all. So in this example, we knew it from because we were writing our function ourselves, and we knew it is a superkey. But okay, it can sometimes be very hard to determine superkeys. But when you're using any higher level language, then you will automatically generate your your source code, and you can probably deduce some properties from this one.
Maybe just to extend. So there's a couple of ways how you can go about this. So in this case here, this is really a low-level representation of a program. So here it's really annotations, and of course, you as the person who annotates that states that as a contract, so you give an assurance that that's the case, which of course is risky for an end-user programmer because the system will rely on that, and if you're wrong, it will make wrong decisions. So that to be clear. However, now there's a couple of ways how you can do that automatically. So one is, of course, and that's what Matthias already mentioned, if you have a higher-level language like Hive or SQL or XQuery or a PIG, then from that language you could deduce it and, of course, encode it accordingly and provide that annotation. Another option is to do that based on some kind of static code analysis. So there's some people actually doing work at that. So the idea here would be that you look at your code and maybe you write your code in a set of functions that have some properties, like you have a concatenation function, and you're concatenating two keys because keys came in, and the function that you're operating is a concat, and then you're having a super key. So you can do it with some kind of static code analysis, even on the PACT level. Although I should say, currently in Stratosphere we don't do that.
Yeah.
One further question on these annotations. If a user manually adds annotations, just in your case, and he's wrong, will this just break optimization, or will it really break functionality? Will it produce wrong results?
You will get wrong results.
Okay.
But for example, we use this for not doing any partitioning step, and then you will just get your wrong result. So you have to make sure that when you annotate something, then it must actually be true. You can leave all these annotations out, and I will show you this how this influences your plan. But once you do your annotation, you really must make sure that it is actually the case.
Thanks.
Okay, any more questions? Okay, so then I'll proceed with the demo. So here I have my plan, and what I did here is I left out all the output contracts. So let's see how this influences our plan. So we have here our map phases where we can say, okay, these are just the independent sets. We do not need any partitioning here. We can use memory channels. But when we are doing our match, we have to somehow partition our inputs. And so in this case, we decided, okay, we partition both inputs. And then we are doing our reduce side join on the reducer side. And so when we're then following, we have to do our aggregation. So what we use is a combiner to do our actual partial sum, which is also in memory because it is also on the same machine. And then we have to do our partitioning again because we have now another key, and we have to partition based on this key in order to do the final aggregation. So we have partitioning for both of our inputs, and we have partitioning for our aggregation in the end. So, but as we have seen, we know something about the aggregation in the end, that it relies on a super key. So, and having this partitioning in the front, we can use this knowledge, and we can say, okay, when we have a partition in our match here, and we're doing an aggregation on our super key, then why do we shuffle our data all through the network? Because if you have all A keys on one machine, appending just another value will not destroy your partitioning. So this is actually what we get when we employ our output contracts. So this is actually the same program, but now with our output contracts. So you see those blue boxes. And we also decided here to do our network partitioning for our inputs for the match. But now in the end, we have an in-memory channel to our reducer. Because as we know this partitioning, we do not have to shuffle. So we probably have to sort the data, but we do not have to partition it anymore because all is already partitioned. And also here we notice that we do not need any combiner because if we are doing our reduce locally anyways, then there's no need for any combiner. So you can see it on the base here. When I click on the several contracts, you will see some properties of the inputs and the outputs of the contract. And for example, for our match contract, we see, okay, we have a key partitioning, which means our keys are partitioned, and from now on, our later contracts can use this knowledge. So this was the use of output contracts. So now how does it evolve when we use different sizes of our inputs? So as we have heard, the join strategy is very crucial for performance. And in order to get the right join strategy, you need to know cardinalities of your inputs and outputs. So what we basically do is we sample the input data, and in order to estimate how the key cardinality will behave. And from this on, we estimate this through all the whole plan as it is done in any relational database, and which is very crucial for optimization. So what I now do is I have shrunk the line item side very much and want to see how this influences our plan. So the line item side, we can see it over there. We have now a size estimate of only 1.2 megabytes, whereas our order side has a size estimate of 1.7 gigabyte. So it is probably much more useful to broadcast the smaller side. And this is actually what we see. So what we do is we're broadcasting our line item side all over the network to our different nodes. And for the much bigger order side, we can just use our in-memory channel. So we do not partition our order side. So we have a lot of less data to ship over our network. So as you may notice, there appeared the combiner. So having our broadcast and not the partitioning of both inputs, we now have to do our partitioning afterwards, because here in our match you see we have no key partitioning in this case, because the order side is just streamed on each node individually, and so we have to do this in the end. But we will probably gain very much by doing the broadcast of the smaller side. And another influence you can see is I've tested this with, these plans were generated for degree of parallelism for 64. So we used 64 mappers, reducers, and so on. And let's see how it behaves when we lower the degree of parallelism. So I'm now using the original size for our relations, which is, I guess, 1.7 gigabyte for the orders and 7 something for the line item side. Actually, it's not that what I've expected. But let's lower it even more. So let's do, we do not want to have a parallelism of 16. Let's do only 2. And then you will probably see that, yes, in this case it's true. As we're having only very few machines which we would have to broadcast our relation, it becomes more beneficial to broadcast our relations. So, and this is what we actually see here. So, even though we have a quite big relation for our orders, we can say if we have only 2 machines, then we have to just copy it to one other, and yeah, so this would probably be better than partitioning both inputs, so that we would have and probably less for the order side, but we would also have to partition the line item side, and there it may be that it becomes more beneficial that we broadcast the order side. And yeah, same as before, we need this additional partitioning step in the end. So we have here also our network in the end. So just to I'll just run the example. So this time with degree of 16, I've chosen to partition the inputs. And I'm hoping that it opens, yes. So we're now seeing, as your question was before, why do we need some spreading of our files to our mappers? This is not what we actually do. We have an in-memory channel from our file directly to the mappers. Then we have, okay, it's very hard to see how these are connected for the match, but as we're doing our repartitioning for both sides, all mappers have to be connected to all reducers, so we have this repartitioning. And then in the end, we can use in-memory channels to our actual reducer, because we can use our knowledge about our partitioning, and yeah, we actually write our data to the output system. And yeah, we can see on the other tab, if it loads, that we have four nodes in our cluster, and yeah, we also could employ some more advanced finding of topologies, but this is we have only a flat hierarchy here in this case. And you also see here in the beginning we had a very huge network traffic because we had to repartition this in the beginning for both of our relations, but in the end we still had no network traffic because we could do the final aggregation locally. Yeah, so I guess this is it. So yes.
So did I understand correctly that the system is optimizing what it does according to my task? Or
yeah,
like, because when you showed this example with when you reduced the number of the nodes and then you said
yes.
like, okay, now it's using broadcast. That means then the system is deciding, okay, broadcast is a good mechanism now, so it
yes.
optimizes for that.
This is the same that we have in relational databases. Mm-hmm. So
okay.
doing cost-based optimization, we have a model how much would the different strategies influence our cost, and then we just pick the most promising or the most robust one. Yeah.
Okay, thanks.
Any further questions? So we're seeing the job finishing, and I guess I hand it over to Sebastian.
Yeah, maybe just want to point out, so if anybody's interested in playing the system, it's available open source, and you can try it out yourself. There's a lot of documentation online, and also very easy install image. So
Yeah, so it's on www.stratosphere.eu. And
You have to put it on again.
Or you put it on the right afterwards.
okay,
Board here.
so this is our website. We have our release available there. We have all the documentation, and yeah, I guess it's very good documented for up to now.
Yeah, just a couple of questions. So, when you have these in-memory operations, one thing I can think of is a failure model. So, how do you deal with this? Do you even materialize data, or?
Up to now, we have only concepts of how to deal with failures. If now any of those nodes fails, the system will crash. But we will implement something more sophisticated, like we call it adaptive checkpointing, where we say, okay, we locate points where we think that it is beneficial to do some materialization of our data, and then where we can later on recover from this point. And yeah, probably you want to say something.
Yeah, so there's one PhD student actually working on this right now. And so there's an initial prototype. So what we have here is, of course, we're writing data. So there's stages at which data is written into the distributed file system, just like in Hadoop. And those points, you have recovery points. So there's some pipelines. Another question is, can you add some kind of fault tolerance within the pipeline, right? So there's always the traditional Hadoop model, and that's here, of course, to write it at some sync point in the file system. There's something that we call ephemeral checkpoints, which is basically checkpoints that are built on the fly while the data is passing through a pipeline. And that depends on really, is your job compute intensive or not? Because if your job is not compute intensive, there's no need to remember it. You just pipeline it by, and the next dam, wherever it is, will collect it anyways, right? So you don't have to worry about it. But if you have a compute intensive job, you have to measure that. And at that moment, you will store, and that's prototyped right now, but it's not part of the open source release yet. You would write that on a side table, and then you can recover from that. And there's a couple of other concepts, of course, along lines of speculative execution and others that we are looking at, but that's business as usual. Yeah.
Sorry. This is a higher level question for all of you guys. It's a brilliant system that I see here. There's something that I don't understand. So far I didn't see anything that cannot be implemented in the traditional Hadoop MapReduce system. But what you present is more elegant and can be reused potentially, etc. And what you say is, look, you don't want to have your hands dirty modifying the combiner, the sorting, etc. From my point of view, I don't see any problems doing this. So what's your take?
Yeah, I'll take the question. So the problem is really how many programmers with a certain skill set you have, right? We saw before the McKinsey report, you need 190,000 people that do that. So the point is, why were relational databases successful, and why are they where they are? It's because it's easy to use and you have an optimizer. The problem is, of course, you could implement all of that in MapReduce just as you could implement everything in assembler. The problem is, would you really want to do that? I mean, join is a huge example, right? I mean, I don't think anybody could meaningfully implement the join in MapReduce, because you have to implement at least 3 join strategies, and you have to implement an optimizer in your program that will decide, depending on what data you have, which of those 3 methods to choose, which means you very often may implement 1 or 2 of those methods in vain, unless you know your data set very well, which you may or may not do. But it's just too cumbersome if you want to do ad hoc analytics queries. That works well if you hand-tune your system like Google does, or also Microsoft to some extent, for a certain amount of queries. But you need this higher-level abstraction, and that's also what shows in commercial worlds, like at Microsoft, for instance, right, where they have come up with the scope language exactly for that reason, which does similar things. The scope is also has the goal to do some kind of optimizations, because in the end, the computer can optimize much better than the human being, right? And particularly if you have repeating tasks. So that's where, I mean, I said, for me, that's an argument like, should we program in assembler? And I don't think we should, or we do, or most of us shouldn't. There's some reasons where it's still worthwhile, no doubt about it. If you write your TCP stack or some things, you might want to, or device drivers, you might want to do some things in assembler. But for high-end data analytics tasks,
you won't, and even more importantly, companies like the analytics or market research companies, they won't find the skill set, and you don't want to educate people in this low-level kind of stuff. I think that's something for engineers, that's something for distributed systems and people, but not for the users of data analytics.